We take for granted how easy it is to conceptualize both large and small numbers using our modern number system, Arabic numerals. This is the number system that is now used worldwide. In previous videos, I showed you how Roman numerals could have been developed and showed you how addition, subtraction, multiplication, and division could have been developed using that more primitive system. Roman numerals are an additive number system. Each numeral in a number, C, X, V, I, each of these numerals represents some specific group of units. As a result of this, to represent more units, we simply write more numerals. To write 10, we write X, but to write 4 tens, we just write that X 4 times. Each symbol stands in one-to-one correspondence with a certain number of units. In contrast, our number system functions through a place value system. Single symbols represent how many ones, how many tens, how many hundreds or thousands are each represented. Our number system has many advantages over Roman numerals. One does not simply need to write multiple M's or multiple C's in order to represent each group of 1,000, 100, etc. As a result, it's much more compact. In the Roman system, when one wants to write a larger number, one must come up with a completely new symbol. If one were to write 5,000s and wanted to write that more compactly, he'd have to come up with a new symbol. In contrast, in our modern system, to write a larger number, you simply add another place value and write a 1 in that higher place value. Our number system is therefore much more compact, it's completely open-ended, and it allows us to represent quantities that we can't even come up with a name for. While our number system is superior to the Roman system, our system is far from obvious and requires several distinct insights to understand how it would be invented. These insights include the use of the concept of zero, which we actually didn't induce even until our last video. So let's understand the kind of thinking that would have been required to develop our modern place value number system here on Inductica. Motivation. I want to introduce our next character. On a beautiful sunny day, hundreds of Babel gather in the city's center. They've all come to witness the Sargon bestow honor upon 2 famous and wealthy traders, Ram and Ark. The Sargon speaks of their achievements in the practice of numbers and the wealth they have earned for themselves and for the kingdom of Babel with their business and trade. He gives each of them a necklace of gold and amber counting stones, a symbol of Marduk's power to understand quantity. In the crowd, Algamesh, a slave boy, looks on. He sees Ram and Ark clothed in garments as bright as those of the Sargon himself. Their faces shine with the same joy and confidence of their ruler beside them. Algamesh has heard of the achievements of Ram and Ark and decides that he will gain wealth and honor just as these men have. Unfortunately, for the time being, Algamesh is just a palace slave. He's responsible for cleaning the palace and the facilities there. But whenever he's not working, he makes a small profit repairing people's roofs and walls. With those bronze and silver coins, he begins purchasing items from people and reselling them for a profit. Through this process, he starts to realize why traders gain so much wealth. They're able to find items for people that those people would otherwise not be able to find for themselves. So soon, Algamesh has more silver than he can count and more tradable items than he can easily remember. And so at this point, he becomes aware of the need for numbers. He understands why traders need numbers. Being a slave, however, he has no one who can teach him the ways of numbers. So as a result, what he does is he sneaks into the marketplace each morning before his duties as a slave, and he watches the merchants in the town square writing out calculations for their customers. Through this process, he learns Roman numerals as well as the 4 operations: addition, subtraction, multiplication, and division. Having no papyrus, Algamesh has to practice his numbers by scribbling in the dirt. But as his business grew, he is able to buy some papyrus, but he finds it to be very expensive. He also found the number system of Roman numerals difficult to work with. It takes up a lot of papyrus to do calculations, and he noticed how mentally taxing it is to keep track of all these symbols on a paper. And these considerations lead Algamesh to the following question. Instead of writing a new symbol for each unit, 1, 2, 3, couldn't I just write a single symbol for each of these quantities? Investigation. Algamesh made new symbols for each of the numbers. Here are the symbols: 1, 2, 3, 4, 5, etc. After a while, though, he notices a problem. He realizes, okay, yeah, it takes up less room, but now I have to memorize all these symbols. By the time he gets to the number 10, he simply writes an X, which is, of course, the symbol for 10 in Roman numerals. But once he does this, he realized that he can write 10 and 1 by simply writing an X and then writing his symbol for 1, and that still keeps track of the number of symbols. Now, he realizes that if he keeps counting, he's going to run into the same problem that he didn't like about Roman numerals. So, for example, if he wanted to write 3, 10, and 5, it would have to look like this. He's still repeating the symbol X for each group of 10 in the number. But then he realizes that he can just use his new symbol to indicate the number of tens. He can show it like this. So we have 3 tens and 5. And so he realizes for the higher numbers, this will also work. So here we see 8, 10, and 3. This is nice because he doesn't have to write out a whole symbol for 50. Remember, in Roman numerals, you'd have to write it out like this, which is a lot of symbols. It's 50, 310, and 3. And so instead of thinking of it that way, he can just write 3 symbols. So as he starts writing higher and higher numbers, he realizes he actually doesn't need to write the X in there. When he writes 9, 10s, and 5, he could just write 9, 5. The first numeral is understood to be the number of tens, and the second numeral being the number of ones. So he doesn't even have to write the Roman symbols in to show what each of the numbers means. Now, once he got to 10 sets of 10, again, doesn't have a symbol for that, but he realizes he can just use the Roman symbol, so he writes the symbol C. The number after that, of course, is the number 101, and he will write it like this. Again, using a combination of the Roman symbols and his own symbols. Now, he would eventually count to 110, which he could write like this, just like a Roman would. But he knew that as he counted, he would need to write combinations of hundreds, tens, and ones. So he realizes that he could continue his old system. So again, he doesn't have to keep writing a bunch of C's for each group of 100. For the number 300s, 6 tens, and 4, he could write it like this. Again, shortening the number of symbols actually needed. Now, of course, it strikes him that he can write the number like this, not using the C or the X anymore. Simply the location of the numbers gives the value of what each of those numbers are. The first number on the right standing in 1-to-1 correspondence with ones, the second number from the right standing in 1-to-1 correspondence with tens, and the third number from the right standing in 1-to-1 correspondence with hundreds. However, he quickly comes to understand that this isn't really going to work, and he comes across this problem as he counts up to the number 300s and 710. So when he shortens the number 300s and 710s, it ends up looking like this, which looks exactly the same as 3 10s and 7 1s. So what is he going to do with that? So here's another example. When he has to write 400s and 8, when he shortens that number, it's going to end up looking like this, which again is a disaster because 400s and 8 looks the same as 4 10s and 8. He realizes that the reason that this sometimes works and sometimes doesn't work is that in numbers like 300s, 610, and 4, there's an actual number in each spot. There's a number of hundreds, a number of tens, and a number of ones. And that allows him to actually see that the 4 represents ones, the 6 represents tens, and the 3 represents hundreds. In contrast, other numbers like 400s and 8, he doesn't have a number for each spot. There's no groups of 10 in this number. So there's no numeral in the second place, which represents tens. And that prevents him from seeing the difference between 410 and 8 and 400s and 8. Now, during his observations of Babel merchants who were doing accounting, he had become aware of the number 0. This was a number that, of course, represented none of something. Algamesh realized that he can put this symbol in any place where there were no units. So if there were no tens, he could put a 0 in the tens place. If there's no ones, he could put a 0 in the ones place. So what would that look like? To write the quantity 408, he could write it like this: 4 hundreds, 0 tens, and 8 ones. In contrast, 4 10 and 8 would just be written like this: 4 tens and 8 ones. So he's able to distinguish those two numbers. So Algamesh continued thinking about how he would represent higher and higher numbers. Once he got to 900s, he found that it would look like this. So 900s, 0 tens, and 0 ones. But what would happen when he had 10 hundreds? Well, he knew that 10 hundreds is M in Roman numerals, so he could just write M000, representing 1,000, 0 hundreds, 0 tens, and 0 ones. But then he realized that instead he could just make a fourth place for the number representing 10 sets of 100. And so that fourth place is the thousands place. He then realized that he would actually never have to write Roman symbols ever again. That this pattern of simply writing his own symbols in a new place could be taken as far as he'd like. So for example, if he had 9,000 and then added 1,000 more, he would have 10 sets of 1,000. So 10 in the thousands place. But since of course he doesn't actually have a symbol for 10, he could just create a fifth place and put a 1 in it. And that would be this number here. This fifth place, of course, he would call the 10,000s place because it's 10,000s. He didn't want to think of another number. He just calls it 10,000s. So this process of opening up a higher place value every time he has 10 units in a given place could be continued as long as he'd like. Algamesh didn't want to name the sixth place. It would look like this. And he didn't want to name the seventh place, which would look like this. He didn't want to give names to these. But he realized that if he ever did have a need of that many places, every time he had 10 units in a given place, he could just change the value of that place to 0 and put a 1 in the next higher place. As a result, this system could be used to write extremely large numbers with ease. Conclusion. In general, we can write the numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to indicate the quantities 0 through 9. When writing a number, the numeral written in the rightmost position indicates the number of units in that quantity. The numeral written in the second position from the right indicates the number of groups of 10 in that quantity. The numerals written third from the right indicate the number of groups of 100 in the quantity. Each successive place indicates a group 10 times larger than the group before it. 10 groups in any one position is equal to the group in the next position higher. Closing remarks. So we can see from this short progression of thinking that the insights that form our number system are not obvious. Algamesh started with a simple motivation. He just wanted to write a different symbol to represent each quantity, 1, 2, 3, etc., instead of just repeating tick marks over and over again. But from there, he came to realize that his new symbols could also stand for the number of hundreds, tens, and ones separately. Once he wrote them in this way, he realized that he didn't need to indicate which number is a number of hundreds with a C and which number is a number of tens with an X. He could just have the number in the third place stand for hundreds, the number in the second place stand for tens, etc. However, he realized that in order to get this place value system to work, he needs to indicate place values that have nothing in them. So in the number 304, he needs to put a 0 in the tens place to indicate that there are no tens. And this helps him keep track of the actual place values. This whole process shows us one of the ways that our extremely effective base 10 place value number system could have been invented. By seeing simple examples of how induction works, by seeing how each insight lays the foundation for the next, we can understand how to use induction better ourselves, becoming better scientists and mathematicians who understand the fundamental process of showing how one's ideas follow from observation. So if you'd like to see the next chapter of this epic inductive journey, hit subscribe or watch the next video to find out how Algamesh uses his number system to invent a new and more effective method of addition. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.